Good morning. I'd like to thank Aviva for organizing this amazing conference. I'm already have learned a tremendous amount, and I probably should have known this before preparing a presentation for this event. But I'm happy to have the opportunity to tell you sort of a story about how a lot of these ideas that Kepler was thinking about have a resonance in modern physics. Specifically, he's looking at the natural world and saying, observing this order and symmetry and patterns and thinking, well, there must be a fundamental reason why these emerge. It can't just be random. And so I'm going to tell you how in some modern questions in physics, we're using similar ideas and with modern tools, both to understand maybe processes that might have happened very shortly after the Big Bang, to questions about formation of things like snowflakes, and then also in some recent work I've done to understand the structure of music theory. So as an example of a system where order emerges out of randomness, here's a video of a snowflake forming. And so there are randomly moving water molecules in the air, and they're condensing together to form ice, and somehow they know where to go to form this symmetric, ordered structure. And so as Aviva briefly mentioned, this is an idea that Kepler thought about in this book he wrote in 1611, New Year's Gift Concerning Six-Cornered Snow or Snowflakes. And as I understand it, this was sort of written as a gag gift for his patron for a New Year's gift. And because he said he couldn't think of anything to give his patron as a gift, and so this is now like predating Seinfeld by like 400 years almost. He said, "I'm going to write a book about nothing, the most mundane, everyday thing you could think of, like a snowflake, and ask a lot of deep questions about why does this order emerge in a snowflake." And at the time, he didn't have the tools that we have today of statistical mechanics and thermodynamics to answer that question, but he had a lot of ideas that are very interesting and it's an amusing read as well. But so today what we would say is, why does order emerge in phase transitions, like from a gas to a liquid to a solid, is that it comes about because of a balance of energy and entropy. Systems have a tendency to go to low energy. They also have, which is usually an ordered state of matter. And they also have a tendency to go to high entropy, which is usually a disordered state of matter. So these two things are in conflict with each other. And so how does a system decide whether to become ordered or disordered? And the answer is the temperature. You could define temperature as how much increase in energy you're willing to trade for an increase in entropy. So as the temperature changes, suddenly the balance shifts, and you go from a disordered state to an ordered state. So we're all familiar with, say, how this happens with the phase transitions between, say, a solid, liquid, and gas. Say, starting in the phase of water, the solid phase of water, ice. It's a very ordered structure. It has low entropy, low energy, and I'll argue it also has low symmetry. And so you might think, well, no, it looks very symmetric. And it looks symmetric, but if you think about, how many ways could you rotate a snowflake to have it look the same? There are 6 ways. You could rotate it a sixth of the way, 2/6 of the way, and so on. But if you increase the temperature, you go to a slightly more disordered phase, water. And if you take that glass of water, you could rotate it by any amount, and it would look the same if you have a circular glass. And so that has much more symmetry, not just the 6-fold symmetry, but an infinite number of rotations. And so that's something that's characteristic of phase transitions, is that as you go down in temperature to more ordered phases, you lose symmetry. Symmetry is broken. It's striking that the lower symmetry state maybe is the more interesting, intricate, beautiful one. And then if you increase temperature further, of course, we get to the gas phase, which is even more disordered than water, than the liquid, with high energy and high entropy and complete symmetry. It looks the same no matter which way you shift it or look at it. So in the context of this talk, I want to use a simpler model than water, because water is actually very complicated when you start digging into the details. So the model I'll be talking about is this square lattice of arrows. So I've got 9 arrows drawn there in a square arrangement. And the arrows will be allowed individually to rotate to any angle. So here they're shown all pointing in the same direction, and that's the lowest energy configuration. So the lowest energy is when each arrow is aligned with its neighbors. The highest energy is when they're opposite their neighbors. So if I allow the central arrow to rotate, as it becomes oppositely aligned, the energy is maximized. We got a brighter color on the plot there. And then as it comes around in a circle, it is at low energy again. So we can use this model to do computer simulations of what happens when you change the temperature. So as an example, at very low temperature, we have a lot of arrows here now, and they're mostly all aligned in the same direction. So that would be a very ordered low entropy state. And again, a low symmetry, meaning that if I make a plot of how many arrows there are pointing in each direction, they're almost all pointing in the same direction. And if I look at that plot and think, well, how can I rotate it to make it look the same? There's only one way I can do it. I have to rotate it all the way around. So it's basically not symmetric. Now, if you increase the temperature, the arrows become randomly oriented. And so this is the high energy, high temperature state. It's disordered. And in this case, I would say it has high symmetry, because if I make that same plot of how many arrows there are with each different angle, it just looks like they're in all angles. And so it's a circle, which I could rotate however I want. So that's a high symmetry state. So going from the high symmetry state to the low symmetry state, symmetry is broken. So anytime you see a system in nature that is lacking symmetry, that has only limited symmetries, you might think that maybe a phase transition was involved in creating that order. Okay, so that's the model. How can we understand this to understand things about the formation of the universe? So let me tell you, what do we know about the universe already? We've made some progress since Kepler's time. And so I'll sort of walk you through the development of our fundamental understanding of the universe, so-called the standard model of particle physics, throughout what we learned in the 20th century. So at the beginning of the 20th century, we would have said there are particles, like electrons, and there are fields, like the electromagnetic field. That's like the electric field and the magnetic field. And the electromagnetic field exerts a force on electrons. The electromagnetic field fills space, and it has some value and direction at every point, and depending on that value, exerts a force on an electron. You also have like the gravitational field, which exerts force on anything with mass. And we also knew at the beginning of the 20th century that in the electromagnetic field, waves in that field are light. There are waves of where the electric field basically wiggles like ripples in a pond. But then, near the beginning of the 20th century, we found out that these waves of light also act like particles in certain situations, and we call those particles photons. So now we've got two particles, but also this wave-particle duality. Not long thereafter, people realized that electrons also act like waves, not just like particles. And so now actually everything is a field. There's an electron field, and the waves in that field are particles. Then we discovered there's a whole lot more particles. 6 quarks that make up protons and neutrons. The muon and the tau particle that don't affect us very much at all. 3 different kinds of neutrinos that affect us even less. These all have different properties. It's hard to see probably, but they have mass, charge, and spin that are all these just seemingly random numbers. Then we discovered there's also more forces. There's a force called the strong force, which has its associated particle, the gluon, and the weak force, which has 2 particles, the Z particle and the W particle. So this is where we were, kind of middle of the 20th century. And it's a very beautiful model. It's very intricate. It works very well. But one thing it has is a startling lack of symmetry. Why? And a lot of mysteries about it. Why are there 16 particles? Why do the particles have the masses that they have and the other properties that they have? The 4 forces behave very differently from each other. Why are they so different? One thing it's hard to notice, 2 of the force particles have no mass at all, the gluon and the photon, whereas the Z and W bosons are extremely heavy compared to the other particles. And so, and if you look at the mathematics, there's also this lack of symmetry that occurs. And so this is this question again, like sort of that Kepler was asking, why do we have the planets we have with the orbits that they have? Is there some fundamental underlying principle that governs this? And so this is where the idea of a phase transition came in. In the mid-20th century, people like Peter Higgs and others had the idea that maybe these forces are actually unified and part of different sides of the same thing. So maybe the electromagnetic force and the weak force are actually two sides of the same coin. And the reason why they seem so different was because there was a phase transition in the early universe that caused them to be separated. And much later, this idea was verified, and we had a 17th particle, the Higgs, which is now a part of the Standard Model. So to explain what I mean a little bit more by this unification or symmetry breaking, the idea is that in the very early universe, right after the Big Bang, it was very hot. And that caused this additional field, this Higgs field, to be disordered. So I've drawn that schematically by, again, this plot that shows, all angles being present of those arrows in a schematic representation. So it's very symmetric, but very disordered. And in this case, this symmetry means that the electromagnetic and weak forces behave very similarly. So a very short time later, about 1/10 of a nanosecond after the Big Bang, the universe is expanded and cooled enough that a phase transition happens, just like a gas freezes into or condenses into a liquid or a solid. And this field undergoes a phase transition. And so now I've drawn this plot where the arrows are mostly pointing in the same direction but still wiggling around a lot. And those wiggles are the particles in the field, the Higgs particles or Higgs bosons. By now, much later, the temperature of the universe is much, much lower, and the Higgs field is completely ordered, and the electromagnetic and weak forces are now completely distinct, and we don't really see these Higgs particles anymore because the temperature is too low for these particles to exist, these wiggles to happen in the field. So at mid-20th century, this was a nice idea. This was a theory. It was maybe a little bit weird. But the question is, how can we test it? And so the way to test it was to create a machine that recreates the conditions of the early universe. And so this is the Large Hadron Collider. And the picture on the right shows the aerial schematic view of it spanning the border between Switzerland and France. This is an enormous device that can accelerate particles and create these enormous energies that were present right after the Big Bang. So they did this, and they found the Higgs bosons, and so that's why we added that extra particle to the Standard Model. So that's an example of how these ideas of symmetry and phase transitions and order can explain the sort of structure of the world we see around us. And it leads to the question, maybe we could go further. Could we just combine two of those forces? Could we extend it to a third, or maybe even all of them? Notice gravity doesn't come into this picture at all because that remains quite a mystery, actually. But could we at least combine the electromagnetic force, the weak force, and the strong force into one? And so this is the idea of these so-called grand unified theories, that there's another field, another particle, and even earlier in the universe, after the Big Bang, there was another phase transition that caused these forces to become separated. And so this is now at the status of nice idea, but how can we prove it? So it's not going to work to do the same thing we did with the Higgs, to build a big particle collider, because the energies required are about 100 trillion times more than for the Higgs. It's already a pretty large machine, so in the near future, that's unlikely to happen. But there is hope to test this theory, because this phase transition that happened right at the beginning of the universe may have left imprints behind that we can still see today. So I'll illustrate that with this simulation here, where I have the disordered state of a bunch of arrows in this high energy disordered state. And we'll see what happens when we cool it down very rapidly. So the arrows start to try to align with each other to go to the ordered low energy phase. But in this particular model, something happens, which is that in some parts of the region, some arrows, say, point to the left. In other parts, they point up. In other points, they point down, and they can't come to an agreement. And so there are these red spots that remain even as it cools down, and you get these sort of swirling patterns called vortices that are stuck there no matter how far you cool this down. And so these vortices or defects should still be here today. And of course, in reality, this is not a two-dimensional picture, it's a three-dimensional picture. And so each of these red vortex cores actually forms a path through space that forms sort of a branching network of so-called cosmic strings. And so this is a cartoon picture, of course, but real astrophysicists can simulate this. And this is a simulation of the cosmic strings from a group at Cambridge. And so they form this network of branching strings that thread throughout the universe. And they should be real physical objects if they exist. They should have mass and energy. They should pull on things with gravity. They should interact with other particles. So we certainly have a hope of detecting them. So far, we have not detected them in our astrophysical observations. But as our measurements become more and more precise, there's hope that we will see evidence for these cosmic strings in the universe and will help us make further sense of the structure that we see in the standard model. Now I'm going to switch gears completely and tell you how the same ideas can be used to understand the structure of musical harmony. So this is some work I've been working on in recent years. And we use the same methods to understand things about the structure of music. And so what do I mean by the structure of musical harmony? Well, a notable thing about music is that, as opposed to sound in general, is that in sound is made up of many frequencies. You could use any frequencies could be present in a sound. But in music, we use this discrete set of pitches. And virtually every musical tradition that I'm aware of does this, uses some discrete division of frequencies to make sound, to make music. And in Western music, we divide the octave into 12 discrete pitches. Why 12? It's a very, very well-conserved property over many, many years, and many cultures around the world also used a 12-fold division of the octave. From those 12 pitches, we often take a subset of them to form scales or chords, and there just seems to be something very fundamental about this particular way of using sounds to make music. So we're going to try to apply the same concepts that were used to understand the structure of phase transitions and the processes that happen there. So whereas phase transitions in physics occur due to this balance of energy, I'm trying to go to low energy and high entropy, I'd argue that there's two factors that lead us to create a system of harmony. One is that we want to minimize dissonance. Some combinations of sounds are pleasant and consonant, others sound harsh and dissonant. And so it stands to reason we would like to hear more pleasant combinations of sounds. But that's not the only thing that we want. If you took that to its logical extreme, you would have just a single pitch that's perfectly consonant, and you would just listen to that. But that might become boring. And so you also need complexity. You need to have enough possible variations within your system of music that you can write lots of different kinds of music that satisfy the composers and the listeners' desire for new and interesting things. So these are two factors that are in conflict with each other. And so which one wins? Well, it's a matter of taste, or you could define that as a matter of temperature. How much of an increase in dissonance you're willing to trade for an increase in complexity. So that's an idea, but if we can quantify this, if we can quantify dissonance and complexity within a system of harmony, then you can use all the same kinds of tools and mathematics that we use to understand phase transitions to understand things about music. So we're going to use the same model, actually, this lattice of arrows. So remember what I showed you before, the arrows want to be aligned with each other. They have low energy if they're aligned, high energy if they're not aligned. In this case, an arrow is going to represent a musical tone. And the angle of the arrow represents the pitch of that tone. So why does it make sense to represent a pitch on a circle? Well, it's because if you double the frequency of that pitch, then you've increased the pitch by one octave, which basically brings you back to where you started. So if you assume that all octaves are basically the same note, then it makes sense to put represent your pitch by an arrow on a circle. How do they interact with their neighbors? Well, the idea is that they should form consonant combinations of sounds with their neighbors. So the most consonant interval is the octave, or unison, the same note played with itself. And that would represent the arrows being aligned, just like they were before, pointing in the same direction. But there are also other consonant intervals that occur at small, simple integer ratios around the circle. So we have 4/3 and 3/2 are the perfect fourth and perfect fifth. 5/4 and 8/5 give you major thirds and minor sixths, and so on. with minor thirds and major sixths. And so we have a similar picture here for our musical pitches, but now as you go around the circle, it's a much more complicated function of dissonance versus the angle with the neighbors. Every time you hit one of these consonant intervals, you get a lower dissonance. And so you can quantify this using equations, and so that's what we've done here. So we're going to use the same model, but instead of the simple preference for alignment, we'll have a preference for consonant intervals. So we can plug this into a computer simulation. And so here what I'm doing is this is now a three-dimensional lattice of tones. And instead of drawing arrows, I'm going to color code each tone. So each dot in that cube is a different tone. And the color indicates its pitch through an octave. And again, I'm plotting how many pitches there are at each different angle on the right. And you can see that this is the disordered state, where there's complete randomness, complete symmetry in that plot on the right. And then this will be a video where temperature suddenly decreases, and we see what happens to both the colors on the lattice and the plot of which pitches are present. So it jitters around a bit, and then suddenly something happens. There's a phase transition. And now the plot on the right it becomes ordered and less symmetric. In fact, there are 12 spikes there in that picture, meaning there are 12 different colors or 12 different pitches present in this lattice. And so those 12 pitches, of course, correspond to the 12 pitches that we use in Western music. So this is just a property that emerges from this simple model, that this 12-fold division of the octave emerges just like the 6-fold order emerges in the formation of a snowflake. So, of course, we don't have to just look at this, because this is each dot there represents a sound. We can listen to it, assuming the AV setup here produces sound. So what I have here is the exact same video I showed you in the previous slide, but now I'm zooming in on 8 particular neighboring tones shown on the bottom there. And so this is the disordered state, where they all have different colors and different random pitches. And now I'll click this and we'll see if it produces sound. So what you heard was the sound going from disordered cacophony at high temperature to something that sounds more harmonious at low temperature. So it's the emergence of harmony as it undergoes this phase transition. And so what's going on here, you notice on the cube has these patches of different colors. So each of those different colors is a region of uniform pitch, and there's 12 different pitches within there. And so the reason why that happened was the same reason that these cosmic strings formed in the early universe. When the phase transition happens, some regions of the lattice begin to order towards one pitch, and other regions start to order towards another pitch, but they can't come to an agreement and never settle into anything, and instead form this patchwork with boundaries between them. The boundaries between them are these cosmic strings. And so in this zoomed in part here, you see there's 2 places where there's 3 different colors around a point. And so you could interpret those as a vortex with a vortex string passing through it. And a place where you have 3 consonant pitches played together is a triad or a 3-note chord. And so you can interpret these strings as musical chords. We can take a closer look at that. In this picture, I've drawn in all of these boundaries, these defects or vortex strings or tonal strings, if you like. And I'll get rid of the dots so you can see the strings better. And so there's this network of tonal strings, these defects within this tonal lattice. And that, to remind you, is analogous to the cosmic strings that are predicted to thread throughout the universe. We can take a closer look at what these strings represent. And it turns out they closely mirror the kinds of chords that are used in music. I've color-coded them here, so the green and red are the common minor and major triads that are very commonly used in music, and then many other chords appear also, like seventh chords and suspended chords, and many other things. And so this lattice is sort of representing the structure of musical harmony, with paths along these strings representing progressions of harmony. So again, instead of just looking at it and talking about it, we can listen to it. And so what I have here is a zoomed-in region of these strings, and the black dot there will move along a path through the strings, and each note surrounding that vortex will be given an instrument, and we can hear the sound of these tonal strings. So this emergence of harmony on these tonal strings starts to lead us to ask, what does this tell us about music, about the structure of music, where it comes from, but also it leads us to ideas of maybe you could use this as a new mechanism for composing music or performing music. And so those are some things that we're looking into now. And so to conclude, the theme of this was, grand unification and universality, which have meaning to everyone, but to scientists have actually specific meaning. And they mean that the order and symmetry that we observe in diverse systems ranging from the early universe to snowflakes to musical harmony all emerge from the same fundamental principles. And I think actually Kepler said it better in his book on the six-cornered snowflake. From this almost nothing, I have very nearly recreated the entire universe, which contains everything, which I think he said as a joke, actually. And so with that, I just want to thank the other people that have worked with me on this project, two students, Hui Din and Ryan Bukele, who are studying physics and math and music here at Case, and Alex Cook at the Cleveland Institute of Music, who is working with me now to translate these ideas into new ways of composing and performing music. And I want to thank the College of Arts and Sciences here in their Expanding Horizons initiative, and also the Coding Scholars Program that have provided support for this. And you can read more about it, the theory of music and phase transitions in that paper there, or visit these links on the web to read more and to hear more. And so thank you for your attention, and I'd be happy to answer any questions.
Thank you, Jesse. Interesting take on musical harmony. A simple question. Your strings, whatever you developed, they correspond to a single pitch?
Right. No. So the strings represent places where there is a sort of a vortex where the pitch changes rapidly around a point. And so since it's a square lattice, there's a square, and a vortex occurs when there's 3 or 4 distinct pitches around that point.
Okay. I see. Another thing, these 12 basic pitches, right, that you derive, depend on the shape of your dissonance function, right? Mm-hmm. How did you find it? And then what happens if you would change it?
Oh, very good question. So that function is calculated based on the theory of the roughness between the partials that make up the timbre of the sound. And so you have to assume a particular spectrum for the sounds. And in this case, I used a harmonic spectrum, like a sawtooth wave. And that's what gives the particular shape of that function. And so, interestingly, if you change that assumption, you get different results. There's the timbre of the instrument goes into that function, and then also a width of how closely spaced frequencies have to be to sound dissonant. And so one thing you can do is you can crank down that width and say, well, maybe some people have a higher tolerance for hearing narrower frequencies. And then you can get things other than 12-fold divisions of the octave, but not just anything. For example, you get like 31-fold division of the octave. And that's something that people use in experimental music. And in fact, historically, going back to notable physicists such as Huygens, have explored music written like that. Other instruments don't have a harmonic spectrum, like percussion instruments. And so if you get rid of the harmonic spectrum, you also lose the 12-fold division, and you're much more likely to get 5 or 7-fold division of the octave, which are, sort of small prime numbers. And that is, in fact, what is often used in other cultures where they have a lot of percussion gongs and cymbals and xylophones and things like that. So there's an interesting angle there in terms of history and, indeed, you didn't ask about it, but temperament, as we were discussing before. As you change the temperature, you can see the historical development of different temperaments also emerging.
I have just one small question I'm curious about. At the end, when you zoomed in on those harmonic strings, if you will, and we got to hear them, is it possible, / has anyone tried to notate some of those things that you hear?
Yes, so that's what I mentioned. I'm working with Dr. Alex Cook at the Cleveland Institute of Music, who is a music theorist and a composer. And we are working on doing what I showed you and actually going a little bit further, including a model of rhythm as well, and bringing in some ideas from regular, notions of composition to arrange these pitches into musical compositions and then also to perform them.
Fascinating. Thank you.
Hi, Jesse. So in your picture on the right there, where you had not here in this thing, but your 12 pitches, some arrows seem larger than other ones. Is there a meaning or significance to that?
So in that case, it's just random. I mean, I think if you had an infinitely large cube, it should be they should all be the same. But one interesting thing too is that I didn't talk about is that if you zoom in on a smaller region, you actually start to see things like diatonic scales or pentatonic scales, because the reason why all these things emerge is because the neighboring pitches are either octaves or fifths or thirds or things like that. They're usual consonant intervals. And if you have sort of a clump of things that are all related to each other by fifths and fourths and thirds, that's sort of what a scale is the set of notes that have a lot of those relationships together. And so that's why if you take this approach of moving along the strings to create music, you actually get things that start to sound familiar. You can have collections of pitches that tend to adhere towards things that we are used to using in musical compositions.
So having created music through this network of strings, it's then tempting to go in and play God and remove all the minor chords or something like that. Have you done that experiment? And if so, what happens when you do that?
I haven't done it. And one of the things that's tricky about it is that you can't really remove them. I mean, you could delete them from the picture, but if you start from the tone lattice, it's an interesting feature of these defects that they're so-called topological defects that you can't remove. If you try to fix it, you'll create another defect somewhere else. And so you almost have to have them. Thank you very much, and thank you for organizing this.